on. Okay, let's turn to the back. Okay, sorry. Okay. Don't have to rush to copy. Let me show you a few things first. Okay, on the last page, the thing that will come to haunt you is this part, okay, which is more the tougher part, okay. NaCl, MgCl, and AlCl3. Okay, I want you to focus on these three words first: hydration, slight hydrolysis, and appreciable hydrolysis. Okay, and I'll explain a little bit more about this. All right. Okay. So moving on, if you look at this, don't draw yet, don't draw yet. This guy that I draw on the left-hand side, the one in green, will never exist. A lot of you are learning transition metals as a casual topic now in school, and probably they don't explain that very well. When you look at aqua complex, right, can only be formed if and only if the metal is high charge density. Okay, I will show you. So this is an example. So you want to have high charge density ions, right? High charge density, high charge small radius. What are the few examples? Mg2+, Al3+, and certain transition metal cations. When you do that, because you have high charge density, then you can attract water to form dative bonds. But if you are not a high charge density cation, right? Example, Na+. I can even give you one more, Ba2+. Ba is group 2, by the way, right? But it's much bigger than Mg. Ba2+, Na+, all these, right, will not form what we call as hydrated ions or aqua complex. Okay, so a lot of you are very bad at this, I'm very sure. If I want to dissolve normal ions, what it would do, right, it will just form ion dipole interactions. So this will not exist. This guy will not exist. Instead, what would Na+ do? Na+ will just do something like that. Because Na+ is a low charge density cation. This is just ion dipole. Ion dipole is one level lower, right? It will never do this. This is absolutely wrong. Okay, please know this, because a lot of you are also always wondering, or if you are not wondering, you are just memorizing. Okay, you need to understand, when do I form aqua complex? When do I not form aqua complex? There's only one criteria: charge density. Low charge density cations, especially group 1, will not. Okay, will not. All right. So what they will do instead, they will not hydrolyze in water. Do you see that? Low charge density of Na+, it does not hydrolyze in water. Hydrolyze in water means that it does not form the hydrated ion. Okay? This means that no hydrated ion, or what we call as an aqua complex. Okay? So you need to understand that. So what it does, right, is that it will just dissolve, like what you all know for since your upper sec days, it will just dissolve to give you this. Okay, so if you want to add on, you can tell yourself these ions will only form ion dipole interactions with water, but not dative bonds. Dative bonds, you must be high charge density. Okay, can okay, Shannon and Danielle, is everything okay so far? You understand?
Yes.
Okay, because today I can ask you a little bit more. Yeah. AQ is what? Where is the AQ? AQ is water. Yeah, optional. If you don't write this, it's okay. Okay. Okay, it's okay. You can just show me the dissolving. Okay, so no need to worry about it. All right. Okay, so going on to this one, I want to pair up these two to discuss. If you focus on AMGCl and AlCl3, right? Can I now remind you that these two are high charge density cations? They can then form what you all have seen in transition metal topic and group 2, group 3, aqua complex. This is called, this has two names. If you focus on what I mentioned just now, it has two names. It's called an aqua complex, or it's called a hydrated ion. Okay, so know your terminologies. Okay, so in this case, if you form a hydrated ion, then we must ask ourselves, which is the one that will affect water more? Okay, so if you are looking at the context, you read through together with me. Hydrated MgH2O6 undergoes slight hydrolysis. This one undergo appreciable hydrolysis. It means the hydrolysis is a greater extent. Difference number one. This difference number one will lead to the consequence. The consequence is, let me use a different color. The consequence is one of them is pH 3, the other one is pH 6.5, which is below. Okay. So what it does is very special. If you use Al at the center, let me draw this as Al. Okay. If I use Al3 plus at the center, right, Al is a higher charge density cation. So what it will do to water? Can you all focus on these two equations? Do you notice these two equations is written the same? Okay, more or less the same, right? So a lot of students will then ask, how come the equation the same? And then I only form one H3O plus or H plus, right? Then the examiner is asking me, how come I would get a different pH? To understand why you have a higher pH is really because actually they have a higher concentration of H plus. And I'll explain to you how come it generates a higher H plus concentration. Okay? It all boils back to one reason. It all boils back to the Al3 plus. Okay? So if you go back to the Al3 plus, okay, I will just focus on one water molecule. I will draw this out. This is going to be a repeated concept for group 2 also. If you look at Al, right, Al has 6 water molecules. It's just like me saying that a guy, that's why I was just joking about this person. A guy has 6 girlfriends. Okay, a guy has 6 girlfriends. But do you think he can focus on the 6 girlfriend all the time very hard? Okay, so although he's very aggressive, very handsome, whatever, he can't focus on 6 girlfriends. He can only focus on one at each time. So what happens here in this polarization concept is that Al3 plus, being higher charge density, it will polarize water to a greater extent. So what will water do? Water will get stretched even more. Okay, so this is the naughty Al3 plus. It will stretch the girlfriend, right? So this is the H2O. It will get polarized to a greater extent. If you are polarized to a greater extent, you will break this bond to a higher tendency, right? So therefore, the H plus will come out from here. So it's actually the H plus that gets generated from the one water molecule. If you focus on this equation, actually it's the H plus. This is the same. H plus is being generated from the one of the H2O water molecules. So it got cut away. And why is it that Al can produce more? It's because Al has higher charge density. So it polarizes water to a greater extent. It will produce more H plus. Okay. So ultimately, if you take a look at here, this is something that they will ask you in structured. If it's MCQ, they will not ask you the reason, possibly not. They will probably need you to know the differences. This is actually a weak acid, right? The pH is a weak acid, but this is actually quite strong to a strong acid, quite near to a strong acid. Okay, so do have that in your consideration. Okay, so this is the simplified equation. I write down this one. This is simplified equation. Okay. So you'll notice that I will not write this equation for MgCl2 because MgCl2 cannot produce sufficiently high H plus to be qualified as a strong acid. All right. Okay. So this is the hardest part they can ask you already for explanation. We will not ask you about NaCl because NaCl is super boring, neutral. I can tell you this page, right? Please focus on this. That's all. Okay, just focus on this part. How do you explain why the pH is 6.5 and 3? That's the thing that you need to be concerned about. Okay. The last one, nothing much to talk about. Okay. Here, you just need to recognize that these two are soluble chlorides. Okay. They happen to be soluble. They don't have to justify why, right? So they are soluble chlorides. They dissolve in water to give very acidic solutions, which is 1 to 2. You can put it at 2, it's okay. Put both at 2, it's okay. All right. The only hard part about here, right, is that you need to focus on the equation. So I leave it up to you. If you can memorize the equation or derive the equation, then please go ahead. If not, I'm aware that this set of equations are probably the harder ones to remember. Okay, so I leave it up to you. Okay, if you can remember, then try to remember. If not, then you will not suffer for it. Okay. The last one here, something very interesting. You see, SiCl4 dissolve in water, right? And then it will regenerate back SiO2 and it will generate HCl. So HCl, all these acids down here, they are what we recognize as pH2. Okay, they are all strong acids. Okay, so the commonality between them is that all of them will produce HCl. Okay, but whether you want to remember the equation, I don't think is the highest priority. Know how to explain is probably more important. Okay, so with that, let's quickly go back to the graphs. Okay, I think the graphs is on the previous page. Okay, so you may want to tell yourself that this is 6, 7. Like how you remember the 4D number, right? 7, 6.5, 3, 2, 2. Previously, we had to remember one, right? 13, 9, 7, 7, so on and so forth, right? So you can just remember these two sets of numbers. I don't think it's hard. You every day just say it one time, you will remember it. Okay? So just try your best. Right? Okay, so let's go back to this front page. Okay, that was what I'm referring to. Okay, so before you go for exam, just try your best to remember some of these numbers and know the reason why. Okay, so we have 13, 9, 7, 2, 2. Okay, I mean this is probably a lame way lah, but so far all these years I don't think I've seen a better way of remembering. Okay, yeah, so just try your best to remember it. Okay, can. Okay, if not, let's go into the exercise. Okay, this one. So you all can start working on it. Then some of you will MCQ question, you did it, you can also ask me. Okay, so I'll give you all around some time to work this on your own. Then I will just entertain some questions from here. Okay, this one very easy one. So you probably try from question 1 to 3 before we move into group 2. Very, very fast one because I purposely fill in the blanks. Okay. Then the next thing you need to do after that is group 2. But we do this first. Okay, just the first 3 questions. The rest you can do at home. Okay, I'll just let you try out the first 3. Oh, done already, then I will send you the check. Okay, I can help you for MCQs. The one that you asked me. Give me a while. Oh, okay. Okay, I will send you the MCQ. Send you the thing. Okay, so let's start working on 1 to 3 lah. If you have done it already, let me know. Then I will send some your the answers. I will still send at the end of the lesson. Where am I now? How come leader you got time to do? I thought usually you got a lot. Wow. Okay.
I come and help you for your MCQs, so some of the ones that maybe I have not fully answered you.
But you answered all already, right?
I don't know lah. I already very bombarded with not by you, but by a lot of others. Wow. Then I feel outstanding. So I'm still answering some of them. So I scared that I never answer some. Yeah, very control. Wait. Yes, it is good. The structure. Yeah, like this and ions with the of delocalized electrons. Yeah, but because they ask you for bonding. So this is your chem memory. You see, this is just a short explanation, but we need to explain structure and bonding. Okay, so not all the answers are here. You need to remember your set 4 chem bonding answers. Okay. Shannon and Danielle, if you want to ask me certain MCQs for period 3, you can also ask me if you have done it.
Okay.
Okay, thanks. Alright, yeah, sure. Thank you. Oh, I thought you finished already.
I finished one.
I thought you asked me so many, I thought you finished.
I already asked you until 19. So I already said.
At least you understand, right? Okay. You learned this last year, right? Is it same for you? You learned this last year?
I think so.
Yeah, lah, which is no learning, no? Right? Because either firstly, it's very long ago. Secondly, after PW, you all usually are not really focused or not in the mood also. Which is normal, As long as not e-learning is worse.
We do gases.
Huh?
Gases. Not only chapter beginning.
E-learning, right? Yeah, but yeah, some schools did it in e-learning, yes. I can remember your school did it. I'm sorry. Gases still not so bad because gases, if you are maths and physics person, I don't think it's that bad. You can still master it. But period 3 actually there's quite a bit of stuff. Okay, I'll check. So let me see how this is low conductivity. Okay. So just do it. Some of it is inside, some of it is not. Okay, I will just flash out a bit. If you are done, you can just check. Okay, so at least I can just show you bit by bit. Okay. Maybe I'll send you all the soft copy lah, so don't worry. Just to get revision. Is it to buy this to blend with this or
Then with what? No, I thought it was the same color.
brown, brown, the sand color, brown. Sandy color.
Freezing on this.
Yeah, right.
Of what of electricity?
Non-conductors. Non-conductors, right? So I know it's, yeah, that's right. Yeah, I know, but it's because I'm putting 3 in the blanks. But it's okay, because A level will not be closed passage. It's just that now I'm just helping you all to save time. Yeah, non-conductors. Okay, if you're not sure, you ask. So try a bit, then
At least until question 3, then after that I will move into the group 2. Okay, so we have a break. Did I own the nail any question? You know, you all must be very careful. A lot of students are getting dengue. Yeah, I don't know whether you all have friends or classmates in school who kena. But recently I have seen a number of cases. This season is the dengue season. It's not because of COVID. It's because it has always been these few months when it's hot and humid. So adults and children also will get. So next time you can, I mean after you study this one, you can also use this. Okay? This one is just later on.
这个好有点难，right? Person is tested in two, or just put it in without discuss. But you probably know, you probably ask yourself how come MG is stronger than NA. Right? Actually, it's not entirely in two. It's also in period 3.
Because you can use NA and NG to compare.
Yeah, so tell me the bonding, like what kind of oxide is it? Yeah, like ionic oxide or metal oxide is also okay, right? But metal is not so good because metal oxides can be also amphoteric.
Like AO.
Yeah, right. The three of them, AL, ZM. So you just write.
So I just repeat again to be naggy. Please study your period 3 from looking at the graphs. If you can explain from the graph, I think you are probably safer. The equation, if you can remember more, then remember. If not, then don't be stressed about it. I think that's not the main focus. Okay, I'll push up a little bit once you're done. Okay, then you can check. If you're faster, you can check the next one. I'll probably talk more about the subsequent question 2 or 3. This one still quite straightforward.
Mr. Lai.
Yeah. Yes.
So when do you use like amphoteric for the Al2O3 or like insoluble?
Wait. You say two things. You say insoluble and amphoteric.
Wait,
Yeah.
yeah, like which one do you use, like amphoteric or insoluble? Because I thought you said cannot amphoteric just now.
Okay. I clarify this. There's a difference. If you say that, if you want to justify, I'll write down in a big sheet here. If you want to justify why is pH 7, then you tell me that it's actually insoluble. So this is the explanation. Insoluble, and it cannot produce H plus or OH minus ions. So why insoluble? You probably can also say that this one has a very high lattice energy or strong ionic bonds. So that's when you talk about that. So insoluble actually only has one context. Actually, it's insoluble in water, pure water. Okay, but if I say that the reaction can react with acids or bases, then that's when you point out to me there is amphoteric. You get what I mean? So there are two different concepts altogether. Insoluble just doesn't break down, dissociate to give ions. But amphoteric, actually it still can react with acid and bases. That's the interesting part. So you throw into HCl equals and NaOH equals, right? It can react. You throw into plain water, right? It just refuses to dissolve. Okay? Okay, so that's when we activate these explanations. You have to ask yourself when is it insoluble pH 7 and when can it react with acid bases. So moral of the story is that I always emphasize this, or last year I would have mentioned this, amphoteric, right, is not the same as neutral. Or rather, it has no connection. Okay? It just happens that this amphoteric one is insoluble and cannot dissolve. Okay? Like buffer, right? Example, if I quote a lame example, you cannot tell me buffer is neutral. Right? Buffer can also be acidic or alkaline, depending on how much you have for each of them. Okay, I will flash this part back. Okay. So I think you can also check that. Okay, there's some simple keywords. The equation, first one must derive yourself. Don't rely on. This one is set 4 work, but this one is need to mark it. Right? Because set 4 teach you, right? Base plus acid use salt and water. So this one is not hard. Okay.
Actually, for the AL2, I don't understand. I don't understand the explanation.
This one.
I don't understand how like high covalent character leads to amphoteric nature.
Oh, okay.
I don't understand the link between the two.
Actually, you can probably not say hence lah, but at least you must tell me it's amphoteric because we are asking you how come Al2O3 can react. They are saying Al2O3 in terms of their acid-base nature. Okay, so here actually I'm more interested in your writing about the structure. Okay, but you don't have to really tell me why. Okay, so going back to here, right? If you are pure ionic, usually you can break down very easily to form ions. But because of covalent character, that's also one reason why this guy cannot dissolve very well in water. Okay. If you recall, actually Zn also, actually Zn below this one, right? So it's high charge density. If you all learn transition metals, right? Then this high charge, that's why actually ZnO is also important. And one of the reasons why we always say is because of the sharing of electrons. Okay, but you don't have to tell me the full explanation how come in this amphoteric. Okay, you have to say, you have to point out that metals with high charge density usually they are not going to be very good at basic acting as basic oxides. That's all. Okay, no need to go into too much detail. Okay. Okay. Right. Let me just forward something to the both of you. Okay. So question C, if you want to do it later, is perfectly fine. Okay, I'm okay with it. So the only one that I want you to be aware about is your question 2 and 3. Okay, just try a little bit from there. Okay, let's get your hands dirty writing out. This one is the top one. You still need this one. This one from the notes. Yeah. This one from the notes. Don't need to worry. You can write it combined. It doesn't really matter. So actually, by right, you can also do it later on without referring. But before it's okay lah, first round okay lah. But later on, let's say you do your school exercise, let's say you introduce some of the, then when you do your school one, then try out, because by after you finish it, maybe you remember later, right? Then you can do without referring. Like your school ones lah, maybe your school has some exercises you can try. Yeah. Unlikely, 这个是 basic and comparing. Comparing can 啊，不是没有。This one is remember I told you the SiO2 diamond, right? I told you the story. Diamond cannot dissolve in soap water. Then SiO2 cannot. Okay. So just now we are at this part. Maybe I just emphasize this part. Just now I told you all the lame story, right? I told you that your mom's diamond ring cannot dissolve in aqueous base also. Aqueous base, which is very dilute. Okay, no reaction. So same thing, SiO2 also cannot react with aqueous base. It's very specific, it's very strong. So you need concentrated. Okay, so this is the equation that I think if you want to, you can mark. But if you cannot remember, then I don't think it's that bad. At least you remember that what it can react with, what it cannot. Okay, equation is just the additional mark. Never stress over it.
You know they say the link between ionic and why ionic oxides are basic.
Wait. Yeah, I know what I'm saying. Maybe just to tell you why the ionic ones are basic, it's because later on when we learn group 2, you will see it. Because group 1 and group 2 metals are considered as alkaline metals. They are under this category called alkaline metals. So Na plus and Mg, right? And also the subsequent one below, when they throw inside water, they will always have to form alkaline substances or basic oxides. Okay, so that's the context. Later we will come across that. Okay, so don't worry. But don't need to explain lah. It's just because of the nature. That's all. We'll explain. Try at least section 2 or 3. Check it out. We are finishing. Oh, your bag like very full, you carry gold to school. Right. You know, every time you all carry heavy backpacks, you will get shorter and shorter. Yeah, it's research proven. Yes, that's why the primary school kids, they always tell them don't carry, because we scared they cannot grow up. Primary school kids still going to go through puberty. So if you are the kind that last time primary school you carry heavy school bag, right? And now you're not very tall, maybe that's the reason also. Really, very scary. Because the back is your backbone. Your back cannot stretch.
I thought you carry heavy, then like your spine or like.
That one is, yeah, correct. Also, that's another the hunchback explanation. But also because your bones are being compressed. So if you are in the growing up years or you carry very heavy backpack, it's not very good. Yeah. By the way, we will all get shorter one over the years. That one is also something you know. You ask your parents, you ask them, were they taller in their earlier age? Yes, they were all taller. They have all shrunken. Yeah. So we shrink for 2 reasons. Because we lose water mass over the years and because of gravity. Yeah, it does. So, we are subject to gravity over like 20, 30, 40, 50 years. A bit, there's some impact. Then second thing is your bone density drops. Your bone density decrease. That's why your calcium is lesser. That's why old people have to eat more calcium stuff, drink more milk. Then you shrink on. Yeah. It's normal to shrink a few cm. Okay, let's take a look at this one. Okay, so if Shannon and Danielle, if you are done, please let me know. Okay, of course, I'll send you the answers, you can check. But part B, please recognize this is the part that you realize your facts are important. Okay, maybe I point your attention towards B. When I look at MgO, right, MgO is considered sparingly soluble, but sparingly soluble is also considered as insoluble. As long as you're not 100% soluble, you are insoluble. Okay, so don't be misled by the words inside my notes. Okay, me saying sparingly is just that I want to use it to explain the 6.5. So if you recall this part, MgO is sparingly soluble. That's why it can give you, sorry, I highlight the wrong one. This is not for this. But MgO is sparingly soluble. That's why later on this will be actually less alkaline compared to your Na2O. If you look at it very carefully, I ask you to highlight those keywords: sparingly soluble, soluble. That's why it led to pH 13 and pH 9. Okay, so please know the reason. Okay. So the M of oxide is definitely not silicon, because silicon oxide is acidic, so it cannot react with acid. Okay. Okay, I'll give you around 5 minutes more. Just try as much as you can until question 3. Then anything not sure, please feel free to ask. Shannon and Danielle also just ask. Okay. If you are asking for MCQ also, you just go ahead. Hey Danielle, how come, do you know how come Anna cannot make it today? She didn't tell me the reason. She told me she cannot come. But do you know the reason?
I don't know.
Oh.
Because we got paper tomorrow.
Huh? Wait, repeat. What paper? Oh, the two. Is it the small test, the BP2 thing?
It's time trial.
Yeah.
Yeah. Oh, what subject?
Chem.
Chem. Oh. Tomorrow is Chem. Oh, okay. Wait. Then, I mean, yeah, but I think some of you Friday you all got stuff, and Friday is public holiday. Yeah, actually Friday I was supposed to cancel the class one, but then cannot because some of them had to wake up on Friday, so I can't cancel. Or I can't postpone it. Not that I do. Okay. Look at yeah. This one, okay. This one must tell me the what solution, not hydrated solution. Now, this solution sounds a bit off, right? The solution is already because of the hydration. Okay? Let me show you. Okay? Hydrolysis to form acidic. But tell me the nature. Yeah. You must tell me the nature of it. So those two equations you copy. I mean, this one is a great copy, but right, this one must be able to write by yourself. This is not the one that's up. Yeah. Come. One. Okay. Oh, this is the metal displacement. So you think about it, your sec 3, sec 4, A level. If you put I show you this one. If you have example, I show you one example, you will surely remember. Let's say I put Mg, okay, I react with copper chloride. But Mg is higher than copper, then it will kick up this one. That's all. Okay. So actually you just infuse it in. Try not to, because Al2, I know Al2 cells is correct, but then later on you will have a hard time balancing. Yeah. Actually it's okay lah, it's possible, but everything will come through. Yeah. So when we say dimerize is, it will dimerize under certain conditions. But by default, we treat it as AlCl3. We just say that you can dimerize very readily because AlCl3 is electron efficient. That's all. But Unless otherwise stated, we just treat it as it is. It's unstable actually. Okay, so it will combine. So we'll just do this. This is something that I asked you on the wall.
That's why the covalent bond is
Which one?
is for AO to close. Because the diamond is conjugate.
In a sense, yes. In a sense, yes. Yeah. But it's not hard to break it. The moment you hit this, right, you will also revert back to their monomers. You can break the limit bond. It's not unbreakable. Okay. The time trial, Shannon, the time trial is what? Test everything or test certain topics?
Everything.
Oh, okay. Because you all don't have BP2, that's why they start to throw in all these kind of small tests. Right. Okay.
Phosphorus chloride is very itself.
PCl, actually either one is fine. If you quote PCl3, okay. So as long as the question didn't mention you are flexible, yeah, you can quote either one. So no issue. As long as you can, whichever you can remember the equation for, then you just mention. Unless they say phosphorus pentachloride or phosphorus trichloride, then it's specific. If they say phosphorus chloride, then anything goes.
I choose you answer is like,
What is it? Yeah.
I choose the and
Oh yeah. Okay. You chose C, but okay.
D,
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 D, 1 and 2. So A, they want to share. A is more reactive than B.
C is the summer, then A and B.
Yeah. So A, oh yeah, I haven't finished it. So B is in acid. But B is in acid. It only tells us that B is okay. B is higher than B plus, correct? So why you put C is
So
higher. You put here C higher. C cannot be squeezed out.
wait, no A cannot be squeezed out.
A cannot be squeezed out C. So
So
C is more
A,
likely.
yeah, so C is higher.
C A B can. Okay. So after B is squeezed out. Then so this cannot happen, right? Because yeah, by right B is B is less cannot. Yeah, C and A can.
C and D can react A
C and
also.
3. So it should be C. Or it's D, the wrong one.
D.
Alright, you're right. I see on this. D plus C. Hello. So okay, alright, because B cannot be split C. So okay, because it's minus. Okay. Okay.
You know, one question is that one.
Yeah. Yes. Because this one is a compound set, then it compile. Okay.
AL is insoluble. If, as in, which one is more? Compound identity knowledge. You are comparing me AL and MG, right?
MG is only MG, MG.
Yeah.
Technically, it's only
So MG, so you must give me two. That's the trick. You need two oxides. That's why I show this answer. Because the answer asks for minimum more than one. So read the question carefully. Suggest possible identities.
Oh,
So MG is sparingly. You are sparingly consider.
oh, it's straight.
Yes. If you are not 100% soluble, you are also insoluble. Right? So sparingly means only tiny bit can resolve that. We don't have a KSP actually. Yeah, MG would actually possible to have a KSP. So if you are not 100% soluble, you are insoluble. So actually these three are insoluble. Despite me keep saying that these two are insoluble, because this is peculiar, MgO is half. Okay, so we still consider it as
That's why
insoluble.
MG always 8.
Yeah, yes, you're right. That's the reason. Correct. Okay. Okay, so you know the idea lah. Okay, as you do the question, you force yourself to refer, you will get it. But the MCQs are probably harder. So this is just a basic foundation set. Okay, it's not a hard one. Okay, so just plow through it, and then after that, when you're free, work on MCQs, and then check in with me. Okay, some of the others they have already asked me, so I just clarify individually. Okay, because I don't have the time, I don't have the luxury of time now. Unlike last year, I don't have the luxury of time to go through the MCQs individually on this topic. Okay. Okay, we can actually start on group 2 soon. Okay, so I'll just put it until here. Okay, so do continue to work on it. Then let's start on group 2 soon. Okay, so I give you about 1-2 minutes mental break. Then we can start group 2 already.
It's only
Yeah.
MG.
Let's provided. Yeah. Correct. Let's provided you can resolve. So MGO can but the question saying what? Let me check it. Or try not to. Simple test. Actually, this one the phrasing should be chemical test. So like if I told the question back to you, you are going to distinguish between carboxyl and alcohol in the exam, you cannot use indicator. Yeah. Because alcohol by right is neutral, although it can act as an acid, but it's still neutral because the pH is lower than the acidity is lower than water. But you cannot tell me add litmus or add universal indicator. Okay, so the simple test, although it's not clear here, is a chemical test. Then you must tell me add some chemicals. So think of a simple chemical, very easy one.
Why 1 mole of CL5 get completely in water, then need 8? I thought I only need like 5. Will just find it.
这个也要neutralize.
Oh, then now straight to me what? Oh no, wait.
Yeah.
Okay, I get it.
You know, right? So this one then okay lah, both then go equation. Yeah, 3H plus. Correct. Okay. Okay, come. Let's slowly move to group 2. Okay. I think I cut you off here. Okay, so we slowly move to group 2. I just open up my set first. Then that's about it. Okay, we finish up the group 2 content. Today I can finish up everything. Okay.
In group 2, I cannot give you I can give you a summary later on, but group 2 is very hard to compress everything in one page. Okay, because group 2 there's some explanation. Okay, so I just put it in these two sheets. Okay, and for those of you who are here, it's just 2 sheets of paper because it's 8 pages. Okay, there's some marking here, some explanation here. So this is probably as complete as you can get. Everything is inside already. Right. Okay, group 2, I got some more writing stuff for you. Okay, so as we go through, just do the writing with me. Okay. I will not do the exercise today. Okay, so that one again, you can try on your own. Then next week, I can probably pick some questions to go through. Then I will start to do organic revision soon, because I don't want to delve so much on this all the date content. Okay, these are the date content. Okay, which you can definitely try alone. Okay, I break down the topic first. Okay, this topic right has 2 parts. Okay, has 2 parts. The first part, right, they are testing you on physical properties. The second part, we are testing you on chemical properties. I will zoom in. So if you look at the assessment objectives, when you study group 2, the first part on physical properties is pretty much repeated from atomic structure. So this part, if you know your content, technically you need to study. What is newer, right, is the one that I highlighted in red. This is your chemical properties. So when you study chemical properties, can I just get you to look at my mini flow chart here? Okay. So when you study chemical properties, okay, chemical properties will test you 3 things. Okay, so Aditya, listen. So elements, oxides, thermal decomposition, 3 parts. Okay, so if you read very carefully, right, the assessment objectives, some of you probably are not very clear. Describe the reaction of oxide water, and last one. So I'm going to just tell you there are three reactions we are looking at. Elements react with oxygen and water. That's the first one you see on the left. Okay, oxides react with water. Okay, and the last one I'm going to share with you is called thermal decomposition. So if you are trying to wonder about the sections here, right, this is the part, right? Elements react with oxygen to give you metal oxides. Elements react with water to give you metal hydroxide. This one very easy one. You probably will know it from your secondary school days. Okay. Then the last one we will test you is, the second one we will test you, right, is how does oxide react with water. So it's very lame, right? Because oxide, if you look at this part, oxide react with water will give you hydroxide. Okay, so this is the third one. So I just covered these 3. Okay, I will talk about the things in detail. All right, and the last one here is thermal decomposition. Thermal decomposition will cover in the last part, which a lot of you are probably very familiar with the explanation. Okay, but I will just point out some things to look out for. All right, okay, so this topic is not that bad. It's really not that bad. Okay, I will say it's easier to study than period 3, definitely. Okay, let's do some simple introduction. So the first part here is physical properties. Okay, I'll probably breeze through the physical properties and I'll highlight to you what's important. This section down here, group 2 metals are alkaline metals. Just now Aditya was asking me a question. Do I need to explain how come Mg gives alkaline or basic oxide? Okay, to be very clear with you, right, group 1 and group 2 metals are alkaline metals. So the both of them, you throw inside water, right, they will give you alkaline solutions. Both of them you burn in oxygen, group 1 and group 2, they will give you basic oxides. Okay, so nothing special about it, but I want to point out to you something special. I mean, nothing special about the most of them. The special one is very new. You may want to tell yourself this is important. Okay, so all of them actually shows an oxidation state, which is all ionic. But do know that beryllium is the one that is special. Okay, so I'm going to just link it up together. If you look at beryllium, later on the last page of the notes, if you bother to turn back, beryllium is actually diagonal relationship with aluminium. This is something that a lot of students don't notice because beryllium and aluminium, right, is split apart by the transition metals. Okay, So to many students, they don't notice that. But it is very important in chem bonding and group 2 that beryllium and aluminum compounds, right, they are very high chance to have high covalent character. And why is that so? Because if you think about beryllium and aluminum has higher charge and smaller radius. Okay? Sorry, higher charge and bigger radius, what am I saying? Okay? Because aluminum is period 3, beryllium is period 2. Okay, period 2, period 3. How do you judge charge density? Charge density is calculated by charge over radius. Okay, so if you look at here, if aluminum charge increase, radius also increase, right? It will end up as similar. You don't have to copy this out. Later it's found in the back part. Actually, beryllium and aluminum has similar charge density. And that's why they like to share. They always like to polarize their anion. So they will always want to distort the electron cloud and then like to form covalent compounds. Okay, so I share with you two classic examples. Covalent compounds here, DCl2 and BeO. Okay, this is very similar to AlCl3, right? Remember? Okay, so some argument points which you already know very well. Smallest radius among them, highest charge density among the group 2, highest polarizing power. Therefore, you distort the anion to the greatest extent and greatest polarizing, greatest covalent character. So covalent character is nothing special. It's just that you have the greatest tendency to want to share electrons. Okay? So I hope this is clear. All right. So let's move on. If you take a look at group 2, right, the part that I want you to be very clear about is the explanation for radius and first IE. Okay. In the period 3 just now, if you all recall, I zoom in on here. You all remember just now I was revising this, or last week I was revising it. I told you, if you're explaining across the period, you always point out to me 3 things. Talk to me about nuclear charge, talk to me about shielding effect, talk to me about ENC. Using the same explanation, you can then tell me the conclusions for radius, IE, and electronegativity. But if you are talking about down the group, never, I repeat, never talk about nuclear charge. Never talk about shielding effect. Never talk about effective nuclear charge. Very important. Okay, only a few schools are still teaching this wrongly. Okay, I don't know which ones now. Okay, it has been some years already. So now all the schools have already, most of the schools have already concurred that when you talk about down the group trends, you always bring in this one. Okay, can I just get you to look at this one? So that later when you look at my answer, you know. You talk about shells. Down the group, period 1, period 2, period 3, talk about shells, number of electron shells. Because you have more shells down the group, okay, I'm just going to write down here, this is down the group trend, down group, okay. Because you have more shells, the distance of the valence electrons is further, okay. And the attraction of the valence electron to the nucleus is going to be weaker. Therefore, your radius will increase, your IE will drop, electronegativity will drop. Okay, this is atomic structure, JC1, first 3 months you must know. Okay, so I'm not talking about anything new. This is old stuff. Okay, you must be very confident about writing this model answer. All right. Yes, but you cannot talk about shielding effect. Yes. I will explain why. Okay. Down the group, right? By right, down the group you have more photons. When photons increase, let me see whether they can see, because I realize it's not. Yeah, okay, they can see. Yeah, so down the group, right, photons increase. Actually, nuclear charge also increase. But down the group, right, shells increase. Actually, shielding effect also increase. The truth, if you bother to check out the university text or the higher level text, right, you will notice that both of them will cancel out. Okay, so the interesting thing that some schools don't point out is that because both of them increase, actually is negated. So effective nuclear charge don't really change so much down the group. but the real argument is distance. Okay, you must bring out it's further away. So if it's further away, then therefore you can bring this up. So my conclusion here is very important. Never talk about shielding effect, and never talk about nuclear charge, never talk about ENC. Okay. Some schools, the old explanation many years back, they say, right, it's because the shielding effect outweighs the increase in nuclear charge. You all remember, they say that, and therefore ENC decreases down the road. We do not no longer use that anymore. Okay, that's an old explanation. Okay, so if you look at my notes down here, you notice I talk about three things: shell, further, decrease attraction. These two explanations is exactly the same. There is nothing different about it. Okay, so that's the trend. Okay, all this is your atomic structure. Huh? Okay, let's talk about melting point, atomization, and density. Before I talk about this, can I get you to look at the data here? If you notice very clearly, right, these three things that are highlighted here, they do not have regular trend. You see, increase, decrease, increase, decrease, increase again, right? Decrease, increase, increase. No regular trend. Very interesting, right? Okay. So when we talk about these three, right, melting point, boiling point, and density, the reason why they have a fluctuating trend is because different metals got different 3D structure, which is not within your syllabus. They have different 3D structure, they have different lattice structure. Okay. But what's probably important for you to know is not to know how to explain these trends because they are not even a regular trend in the first place. Okay, is this card. Can I show you down here? So what you need to know, right, is that when you talk about group 2 and group 1, you need to tell me how come group 2 metals is stronger than group 1. And that's something you have learned in period 3. We have learned that magnesium is stronger than Ni, right? It's harder. So why is it? Is it stronger? Because it has stronger metallic bonds, more delocalized electrons. This explanation was used before just now, right? So you don't have to tell me about down the group. You just tell me how come group 2 will trash group 1 in melting boiling point. That's number 1. Okay. Number 2, delta H atomization. Group 2 will also trash group 1. Why? Because if you are looking at atomization, the idea here is that we are trying to form atoms from solids. Okay, that's the meaning of atomization, gaseous atoms. So you look at this equation, I'm trying to transform a solid metal into a gaseous metal. This is endothermic in nature. Endothermic, right? So I'll just write down here. Huh? So if this is endothermic, it uses energy. You want to transit something from solid state to a higher energy state. You take in energy. So you'll realize that same goes for here. If you want to transit from solid to gas, you need to break the metallic bonds. And it's going to be harder also, as what we mentioned just now. Okay, so delta H atomization of group 2 metals are going to be higher than group 1 metals as well, because of stronger metallic bonds. Same reason. It all boils back to the same reason. Okay. Last but not least, density. Are they denser than group 1? They are. Why? Because if you focus on this very simple diagram down here, this is like Na, sodium. Sodium is fat plus it's only singular plus charge. But Mg is very small. Mg is small and each of them is 2 plus. So the same reason applies. If you are looking at density, that also hints to you that group 2 metals are definitely harder, right? Harder than group 1. And that's also the same reason why group 1 metals are very easy sliced apart. They are very soft. Okay, so the spaces between them is quite a lot. There's a lot of gaps. Okay, so just bear this in mind. Okay, someone just got kicked out, as in not kicked out, as in just accidentally dropped out. Okay, come let's take a look. Yeah, accept her back. You know, sometimes I never accept your back because I never even hear the thing talk. Then I say, and then I never go and check how come this number is always the same. Usually, by right, I must keep monitoring this number, but I mean, I will not keep looking at this number so small. Yeah. Okay, come. Okay. So physical property done. Can we move into the new content, which is chemical properties? Okay, let's revise that together. Aditya, we're on page 3 already. Okay, so if you look at chemical properties, just now I share with you 3 things you need to know. Let's revise. We need to know the metals, we need to know the oxides, we need to know thermal decomposition. So let's cover the metals first. Something very important here, this will govern the rest of the chemical properties. As a general outline, please know this, because down the group, the metals get bigger, right? Mg, this is Ba. Mg is period 3, period 3, period 4, period 5, period 6. Barium is period 6. So the general argument here is the same. Although it's not written down here, what we are trying to say is that down the group, the size increase. When the size increase, the distance is further apart. And we probably need to recognize down the group, right? It's easier for me to lose electrons. Do you see that? It's easier for me to lose electrons because the distance is further, more quantum shells. So this brings to us the rest of the model answers really. Because if your distance is bigger, more easily losing electrons, that means to say right down the group, it will actually become more easily to be oxidized. So all these words are one and the same thing. I'm just paraphrasing them. So if you want, you can just have a quick jot. Stronger Ra down the group, they have a higher tendency to be oxidized. They are also more reactive metals. Exactly the same for group 1. Okay, I don't even need electrochem to justify. A lot of y'all keep saying, is it because of the electrochem values that tells me? No. It goes back to the first thing that we mentioned just now. It's because down the group, further distance, electrons are further from the nucleus, less attracted to the nucleus, more easily lost. That actually tells us that metals, right, down the group, we don't even dare to deal with all those cesium, francium, very scary. Okay, we only dare to touch like Na, Mg, because these are no metals that are not very dangerous. Okay, but down the group, the metals are very, very dangerous. Okay, so one potential question to share with you here, if you read this, explain why the reducing power increases down the group. We can ask you this in different ways. Why is it that metals have a higher tendency to be oxidized, or why the metals are more reactive? Okay, so let's take a look at the standard model answer. Now the group, valence electrons more easily removed, weaker attraction, right? So the metal is more easily oxidized, reducing power increases. Okay, so this kind of explanation is usually 2 marks only. Okay, 2 to 3 marks maximum. Okay, you will not go beyond that. Okay, so please know your standard answer, right? Now you know this, you have to use this concept to apply for the rest of the context here. Because what we're going to discuss next is 2 things, right? How can metals, I'll repeat this again on the front page, how can metals react with O2 to give you metal oxides? Okay, and how can metals react with water to give you metal hydroxides? Okay, so these are the 2 things they will test you for elements. So if you are looking at metals with oxygen, they're just going to be oxidized very clearly, right? So you either leave it exposed to air, typically you will burn it, right? So when you burn it in oxygen, excess oxygen, they will form oxides, okay? But the fundamental thing that you should observe, right, in the formation of oxides is actually a oxidation reaction. In fact, this is a redox. This is a redox. Because the oxygen is reduced and the metal is being oxidized. Okay? So you ask yourself, how come the metals become more and more reactive? The flame test is not needed. Okay, you can ignore that. The flame color is not needed. But at least you must tell me, how come the reaction gets more reactive, right? It's going to be more reactive down the group. Barium will actually ignite spontaneously. You don't even do heating, just put down there, right? Bam, explode really. Okay, burst into flames. That's the reason why, because electrons are further from the nucleus. Okay, so this one I will not harp on it. It's supposed to be very manageable. Okay, now I look at this one. Something exceptional here, you may want to asterisk this for yourself, is that for the more reactive group 2 metals, right, they do have a tendency to form this thing called a peroxide. So peroxide, right, is the hydrogen peroxide, the H2O2. So this is the peroxide anion. For some of you who are not very sure, this is actually rightfully the peroxide anion. Okay, so peroxide anion, if you simplify it, then it will be O minus. Okay, but this is not peroxide. Peroxide is O2, 2 minus. Okay, and you will then notice this is also a redox, right? So it's only peculiar or specific to certain reactive metals at the bottom because they are able to lose electrons more. Okay, so that's something that you need to see for yourself, right? Okay, the last one here, I don't have to stress over it. Secondary school learned this before. You all learn sodium, group 1 metals. Then they ask you, how do you prevent sodium from reacting on its own, store under oil? Because sodium will react with oxygen and water as well. Okay, so this one I will not mention. Okay. Okay, let's look at the second one. Just now we learned about metals with oxygen, right? Now we learn metals with water will give you hydroxide. You see that? So if I look at the context, right, it's also the same, you know. We are actually asking you, how readily can the metal be oxidized to form M2 plus, the same as just now. If you look at the trend, right, you probably can tell yourself, you see, Mg got very slow reaction. Mg don't really like to react. Why? Because Mg is very small. It doesn't really like to lose electrons. Okay? What about barium and calcium and strontium? You don't even need to stress over it, right? You just throw cold water and you'll get more and more reactive. In fact, barium is the most reactive among them, right? It's going to lose electrons most readily. Okay? And that's first thing to know. Second thing for you to know is the solubility. This one is not just tested in group 2. It's tested in energetics. If you know nuts about this, then quite serious really. Because if you think about solubility, I did mention in period 3, right? Solubility depends on one very important factor, okay? Solubility depends on this equation. Delta H solution equals to hydration minus LE. And if you recall what I taught you all before, if your lattice energy is very high, like negative 10,000, I repeat, negative 10,000, very high lattice, strong ionic bonds, what will happen to your solution? It will be very endo. If you are very endo, that tells you that substance is very hard to dissolve. Okay? Well, on a simpler note, right, I just want to point this out to you. If you look at MgO2 and BOH2, you also know, right, because the lattice energy for MgOH2 is the highest, smallest radius. Right? So if you have smallest radius, the magnitude of lattice energy is the highest, therefore it's the hardest to break down. Okay, so that's also the reason why you look at here. Can you all notice this equation? If you bother to circle this and then you can check this arrow here, slightly soluble. But if you look at the arrows here, 100% soluble. Okay? It's not because you mark, right? It's because you know the chemistry reason behind it. Okay? So lattice energy affects solubility directly because solution means that you can dissolve to form ions. Okay? So that's the reason why magnesium hydroxide is not that soluble. Okay? So it's not a strong base anyway. Okay? Okay, let's move on. So before I move on to the oxides with water, recap what have we learned so far. We have learned that elements can react with oxygen to give you oxides. Elements react with water to give you hydroxides. What do these two depend on? The reactivity of this actually increases down the group. Okay, I'm just writing this out for recap, okay? And why? Because greater ease of oxidation. The same applies for both. Okay, greater ease of oxidation down the group. Because for these two reactions, we are talking about M to M2 plus. Okay, so you don't have to stress over this. Okay, you just need to remember your fundamentals. The last one that I will cover is how do oxides transform into hydroxides. That one is a bit different. Okay, so if you are already the oxide, right, you throw inside water, yes, it is supposed to give you the metal hydroxide. So if you know your basics very well, right, okay, let's not say basic because basic is used here. If you know your fundamentals very well, then this is a basic oxide. You throw inside water, it will give you a alkaline solution, rightfully speaking, right? Because these are alkaline metals, alkaline metals, basic oxides, alkaline solution. Okay. Okay. So now I want you to just circle these three things out. I don't really care about the content down here, but I want you to tell yourself how come there's a disparity here. BeO insoluble, so totally cannot break down. MgO partially. Just now Aditya pointed out to me, right, sparingly soluble, right? Sparingly soluble, yes, it's insoluble, but here we need to justify later why the pH is 9. So we need to say that, oh, it does give me some low concentration OH. Then the last one, right, is calcium oxide. Calcium oxide very soluble. Okay, very soluble. Why? Because if you go down this trend, or at least you go across the trend here for the group, please know. If I exclude barium, later I'll talk about barium. If you focus on the trend for Mg to barium, you will notice that they have higher and higher lattice energy. I mean for Mg. Mg is the highest. This one is the lowest, right? So Mg is the highest lattice energy, strongest ionic bonds, therefore it's the hardest to dissolve. Same reason as what we discussed just now, right? Barium oxide is the weakest lattice energy, therefore it can dissolve very well. So, and that's also the reason why later barium and calcium oxide will give us very strong bases, because the solubility is high, weak ionic bonds. Okay, so these are things that you need to draw together from your chem bonding. Other than that, the observations I'm not so concerned. Okay, that one you can go and read through, right? Now I talk about the special part here. Okay, focus on this part. Okay, the last part here. How do you explain the barium especially? Okay, so one thing I want to bring your attention to, right, is that to explain how come barium oxide and also MgO is not very soluble. Okay, one of them is barium oxide is insoluble, MgO is sparingly, right? Well, sparingly, just now we say it, sparingly also can be classified as insoluble. Okay, so to explain why these two are insoluble, right, we use two reasons. Reason number one is that these two oxides, being the top of the group, right, they have the highest covalent character. So if you have the highest covalent character, you do not have a tendency to break down the ions so much, because covalent character means that you want to stay as molecules. Okay, so that's reason one. That's the first reason. Both of them have the higher charge density. If you all know what I'm talking about, right, barium oxide is actually treated as simple covalent, but MgO is treated as a giant ionic with covalent character. You've learned this in period 3 also, right? So we do mention that actually both of these guys got significant covalent character. It's just that MgO happens to be classified as giant ionic. Okay. The second thing that you probably need to know, right, is that using the lattice energy formula, LeQQ R plus R, they have the largest magnitude also. Okay, so the ionic bonds are the strongest. They are also the most covalent. So it's a bit of a paradox. Okay, because previously when you all learn this, you all don't really think about it. Okay, so something can be the most ionic, yet be the most covalent at the same time. And this brings to your attention, I think, the idea of Al2O3, if you all remember. Al2O3 is the most ionic, among the three oxides, and is also the most covalent. Okay, so talking about Al, can you see this yourself? Beryllium oxide, just now I was sharing with you, right? Beryllium oxide is the same as Al2O3. They are cousins, or they are like siblings like that. They have a diagonal relationship. So I did ask you to know this, right? From Sec 4, Z, zinc aluminum lead. But the fourth one is beryllium. Beryllium is amphoteric also. So because of the fact that it shares a diagonal relationship with aluminum. So if you look at the formula, right, they actually react quite similarly there. You see, beryllium can react to give you the BeOH4. And you think about aluminium, right? Aluminium is also the same. You can also form this AlOH form. Okay? Okay, so that's the complex we've learned in KSP. All right? Okay, that's all for this part. Can I cover this thing, finish out with this part called thermal decomposition? This is the last reaction for the day. Okay. Okay, thermal decomposition is something that I think all schools will have tested by now. Okay. I'm very sure you have gone through a test with this explanation already. Okay, but I probably will value add to this by telling you this part or remind you what's the difference between thermal decomposition and melting. A lot of you are still very confused by this, or some of you might be using the wrong explanation in the exam. So if you want, you can write this down, okay, so that you don't make the mistake in the exam. Thermal decomposition, right, is this process. I'll highlight here. You're actually breaking something down to form a ionic byproduct and a gas. This is that means one item break down into two items. But melting, right, is this one. This is melting. Melting is simply take the ionic compound like electrolysis, you change it to molten state. Okay? So can I revert back? Yes. If you are thinking about this, more accurately speaking, this is actually reversible. I can actually change it back to the solid by cooling it down. Okay, so ionic compounds you cool down, it's the same ionic compound, right? So this is reversible for melting. But chemical or thermal decomposition is a chemical reaction that is irreversible. Very important. So when you explain this, right, some of you always, or a very small percentage of you, right, will always use the Chem bonding explanation for thermal decomposition. We always see that. Then you all will tell me, oh, thermal decomposition depends on lattice energy, the strength of the ionic bonds. That is very wrong, because thermal decomposition is only involved in breaking covalent bonds. You're only breaking away the CO2, right, from the existing CO3 2 minus. Did we break the ionic bonds? No. Do you see that this one has ionic bond? This one also has ionic bond. We never break the ionic bonds. It was there all along. You just broke off part of the anion. But melting is breaking ionic bonds. So if you are talking about breaking ionic bonds, then the whole argument will hinge on lattice energy. That means you must quote the lattice energy formula and talk about it. But right, if you talk about thermal decomposition, then it's no longer about lattice energy. You must bring in this concept about charge density and polarizing power. Okay? So can I show you the, okay, once you're done with this part, I'll show you the bottom explanation. Okay, this part is pretty manageable. You've gone through it a lot of times. Okay. So now if you observe the data, you probably can tell yourself, okay, by the way, this melting, right down, this melting, this is thermal decomposition, which is a chemical reaction, right? Okay, in A levels, by right, we test carbonates. But for your prelims and your additional questions, sometimes we like to expand a bit more. So they might test you nitrates, they can test you iodates. So don't be restricted to just carbonates. Okay? So now you take a look at here, the data. Can you see this? Down the group, do you notice? You need a greater temperature to break this down. Greater temperature, right? What does it mean? If you need a higher temperature to break down the substance, that means down the group is going to be more stable, right? On top, it's not very stable, okay? So how do we explain that? Okay, let's take a look at this part. The keywords are the ones that we have talked about in covalent character, very similar. The idea here is this: if you are a small metal cation on top, example, this is Mg 2+. Example below this is barium 2+. What happens is that if Mg2+ is a high charge density cation, because it's smallest, it will also have the highest polarizing power. So it will distort this anion to the greatest extent. So what happens here? In this anion, the covalent bonds in the anion are weakened to the greatest extent also, because you stretch the bond, right, to the greatest extent. Okay? But whereas for here, you don't really stretch the anion, right? So if you are looking at this context, please bring out the idea of polarizing power. High polarizing power, low polarizing power. Very weak bonds, covalent bonds, of course, very or stronger covalent bonds. So you have to bring out this one. Anion, this is the sentence that some of you need to quote. Anion become less polarized, the bonds are weaker to a lesser extent. Okay? This part, some of you don't really explain very well sometimes. Okay? So just to finish this part up, okay, this is the visual idea. It applies for carbonates. If you are thinking about carbonates, it is the same concept. Maybe I draw this out. This is a carbonate. Okay, CO2 minus, CO3 2 minus. So bear in mind, can you see this? The ionic bonds didn't break. Whether it's carbonate or nitrates, the O is still bonded to the Mg. But what you are truly breaking is actually this part. Okay, so this part will become CO2. This part will become NO2. But your ionic bond is still intact. That's why this is a chemical reaction. Okay, a lot of you have this idea that melting is a chemical reaction. No, melting is reversible one. Okay. Okay, so that's all for this part. I believe most of the answers are pretty much something that you've gone through. Okay, the last one that I want to point out to you is here. This one is extra. I imported this from energetics. So let's end on with this one, then you can be on your way to rest really. Okay. This is a question that we can potentially test you for energetics. Okay. You may or may not find this in group 2 notes, okay, because they may not put this in. So let's say if the question tests you, they show you this data. Solubility of the sulfides actually get more and more insoluble in water. Okay. So when you think about this, as what I've discussed with you, you all will start to think about lattice energy because these are ionic compounds, right? So you all will definitely quote lattice energy, right? The problem about here is that if you think about solution equals to hydration minus lattice energy, and down the group, what happens? Down the group, the radius increase. So when you check this out, barium is bigger than Mg. So what can you conclude from here? If barium is bigger than Mg, I shift this back here. Can you see these two equations? This equation and this equation, right? The radius will increase. The R increase, the R increase. So when the radius increase for hydration and lattice energy, can you tell yourself, actually both of these values will become lower? Okay, because the radius increase for both of them. Are we okay so far? So that's an important observation because this explanation is not easy. Lattice energy would go down, less exothermic. Hydration will also go down because down the group, the size increase. That's all. But what's next is the one that you need to try to explain. So what happens when both go down? You realize that these two values are both exothermic. Okay, by default, they are both exothermic. So this will become less exo. This will become less exo, right? So the idea is that if both of them become less exo, right, how then do we conclude that delta H solution is going to be positive? There is only one way. The one way, right, is to tell them is because you observe that hydration actually decreases much more than lattice energy. This is the hard part. Okay, so both of them drop, but hydration drop more. Okay, so you just think about it in terms of numbers. Both of them are negative, but the first term drop much more. Okay, become less exo. Sorry, less exo means more positive, right? So it will actually become less exo. So it's because of that, right? If lattice and hydration decrease much more than lattice energy, that's why your solution become less exo or more positive. And that also tells us that you are less soluble. Because if something is delta H is more than 0, that thing is insoluble. If delta H solution is less than 0, that thing is likely to be soluble. Okay? So this is the part that I'm more worried about. If you're not very sure, please go back and read through this again. Okay, you probably will not understand this on the first understand this completely on the first count. Okay, so read through this part again. See whether you understand what I'm trying to say. Okay, because the values will actually both become less exo, but one of them will drop much more. Okay, so talk about this. Okay, anyway, it's an energetic question. So be prepared that we can ask you to explain in terms of data. Okay, so you may not need to quote all the information, but you need to be able to tell me how come the trend is like that. Okay. Okay, that's all I have. The last part here, last 2 pages here is not that crucial. Okay. The only thing that I want to repeat again, which I've talked about, is this one. Beryllium aluminum is diagonal relationship. Can you just learn one last one for the day? The last diagonal relationship is lithium and magnesium, which some of you may not know. Can you just highlight it for yourself? Because we can actually tell you that lithium and magnesium can have very similar chemical properties. You all learn about magnesium, right? Magnesium is group 2, right? Can we test you lithium in group 1? We must, because lithium is diagonal to magnesium. So that tells me something. Okay, you can jot this down. Lithium and magnesium also have similar charge density. Similar doesn't mean equal, or similar means aggravation about this, quite near. So the same thing, beryllium and aluminum also got similar charge density. And that's why later on their reactions and their chemical properties are quite identical. Okay, so this can be tested for application question, lithium and magnesium. Beryllium and aluminum, I think most students will know lah. Okay, so if you don't know, then please know it. Okay, because this tested in group 2. Okay, can. So that's all I have. Next week, right? Next week I will go through as in I'll not go through everything. So next week I'll probably just pick selected questions in the group 2 revision, structured question to go through. Okay, I will not go through everything. So I'll just get you to try, okay, write it out, force yourself to write it out as a revision. Okay, because inorganic you can only study by doing a lot of referring and writing. Okay, you cannot just read it, you probably not remember it. Okay, then next week onwards, I will probably start to talk more about the JC1 physical chem topics and revise a bit of organic already. Okay, we don't have much time now. Okay, this year I have much lesser time for prelim revision. Usually I can do like 2 months or 1.5 months of prelim revision. Okay, but right now not much. Okay, so I probably can revise for 3 or 4 lessons. That's it. After that, of course, then we will do the more thorough revision because we have time. Okay, can. Okay, so Shannon and Danielle, that's all. Okay, good luck for your test. Please don't please don't fail it. Okay, try to pass it lah. Okay, not that don't fail lah, but try to pass it well. Okay, pass it, then score your E and above, then good. Okay, that's all. And if anything tonight, you can ask me, but I also try my best to answer. Okay, because I also want to clear. I'll clear your questions first. If you don't have any, because you all got test. Okay, then the rest can read. Okay, and okay, so I'll see you all. Okay, bye.
Bye, Mr. Lai. Thank you.
Bye. Thanks. Okay, bye.